my name is Terry. In this video, I'd like to talk about solving double integrals over general regions. If I could draw your attention to the screen, we're going to set up our own double integrals this time based on what the bounded region is, and we're going to solve the iterated integral once we set it up ourselves. There are two different methods you can use. So double integral means you're integrating with respect to variables x and y. So you can integrate the x first, then the y, or you can integrate the y first, then the x. When you actually have to set this up yourself, you're going to first want to sketch your boundary so you can see which way may be easier to approach the solution that you want to work through. In many cases, and just about many cases, you can do both ways, okay? Type 1, type 2, and you can do both ways, but many times one is easier than the other. So we're going to do two examples, and the two examples that we're going to do, we will do type 1 and type 2. Type 1 is where you're going to have vertical slices. You're going to want to integrate the y component first, then the x. So integrating the y components, well, if you have vertical slices when you draw your base and draw your diagram, if you're going to utilize vertical slices, then your variable bounds are going to be on the inside. You're going to have your y equals, and then your inside bounds will be a function of x. And then your outside bound is going to be point of intersection to point of intersection along the x-axis. Okay, so you're going to have constant bounds on the outside, but they will be put together by using points of intersection. Your type 2 is where you're going to integrate the x component first, then the y. Integrating the x first, then the y. So in your diagram, that would be evident when you're drawing horizontal slices. So horizontal slices will allow you to write your x equals as a function of y when you're utilizing horizontal slices. So your inside bounds are going to be x equals as a function of y. You're going to have y bounds on the inside, and then the outside bounds are going to be points of intersection, but along the y-axis, the y-coordinates. So this is what the general rules are for your type 1, for your type 2. So we're going to do two examples. Your first example is, it's written on the board here. So for example 1, let's take a look at this, and we're going to try to utilize type 1 and type 2. Let's do this one both ways. You can see many of the problems in the book, it will just tell you to find the volume of the solid generated by this. So find the volume so you don't always have to do both type 1 and type 2, but we'll do this just so you can have an idea of how they both work. So we're going to set up a double integral. The surface is x squared plus 2y, all right? dA, so dx, dy, dy, dx. We'll do it both ways, as I said. So your boundaries are y equals x cubed, and we want just pretty much in the first quadrant. Okay, so positive x values, which with these bases, you're going to just deal with in the first quadrant. So let's start with setting this up and working this through using the type 1 method. So type 1. Okay, so we're going to use this set this up using the type 1 method. So let's draw the base. Okay, so we want to definitely draw the base first in the xy plane. Okay, so here's your x-axis, here's your y-axis. All right, so y equals x. When you draw y equals x, here's y equals x. Okay, y equals x to the third power. So y equals x to the third power. So we're just kind of coming through and getting our first. All right, so here's y equals x. Okay, and this is y equals x to the third power. So this is our base right here. All right, so we're going to need the points of intersection. Okay, so we're going to need to get the points of intersection. The points of intersection are going to be utilized in our bounds, in the outside bounds. So points of intersection of these two curves, you're going to be able to generate that by setting the curves equal to each other, by setting x to the third equal to x, okay, and then solving this algebraic equation. So it's a polynomial equation. So to solve a polynomial equation, we're going to want to move all terms to the one side and get a 0 on the other. All right, and then factor out the x. Okay, so you have x squared minus 1. And then when we solve this, you have x is 0. You have x would be plus or minus 1 for these bounds, okay? So in this case here, okay, so we have 3 points of intersection, but we're only dealing with the positive x values. We're not dealing with anything over here in the third quadrant. So one of our bounds right here, one of the points of intersection will be 0, 0. Whatever the x coordinate is, the y is the same thing. okay? And then this one right here would be at a positive 1, so this ordered pair right here would be 1. Well, whatever x is, y is the same thing, so that would be at 1, 1, okay? So we pretty much have all the information here we need to set up our type 1, okay? So our type 1, so we're going to set up a double integral for type 1. We're going to set up our double integral. The integrand is x squared plus 2y. So remember, type 1, we want to integrate with respect to y first, okay? So with respect to y first, so that means when we draw we're going to draw vertical slices here, okay? So drawing vertical slices here, our inside bounds are going to need to be written as a function of x, okay? So to write the inside bounds as a function of x, okay? Take a look at the diagram with vertical slices. We want to go from low to high. So we want to go from x cubed to x. So the lower bound, just take a look right here at your vertical slice, is going to go from x cubed to x. You can see it right on the diagram. Okay, so diagrams help so much. Help you see, get a picture of what you're doing. Okay. Then after we take care of the integration with respect to y, dy, we're going to want to integrate with respect to x. Okay, so integrate with respect to x. Well, then the x bounds, the x bounds your horizontal. All right, and you're going to go from the x coordinate to the x coordinate, from the x to the x. So your outside bounds are going to be from 0 to 1, 0 to 1. Those would be your outside bounds. Okay, so here is how you would set up your double integral to solve this over the given boundaries. So, okay, now to evaluate, and if you remember when we were last video, when we were evaluating iterated integrals. To evaluate, we're going to start from the inside, okay, so work from the inside to the outside. So we want to start by integrating with respect to y. We're going to integrate with respect to y first. So you have 0 to 1, we'll take care of that shortly, okay? Integrate with respect to y, so x is treated as a constant, so x squared, and just multiply that by y. Integrate with respect to y, so you integrate 2y with respect to y, you get 2y squared over 2, and the 2's will cancel, so y squared. Here's the integral with respect to y. We want to evaluate this from x to the third to x, okay? And then we'll evaluate with respect to x afterwards, okay? Fundamental theorem in calculus now. So fundamental theorem in calculus, all right, let me just move this out of the way here, all right? So fundamental theorem in calculus, we are going to plug in the upper bound, okay? So we're plugging in for y, so when you plug in the upper bound for y, you're going to have x times x squared, so you're going to have x to the third, okay? Plug in the upper bound, okay, plus x squared, all right? Then we're going to plug in the lower bound for y. Y was our variable, so we're substituting for y, so x squared times x to the third power. Here you're going to want to keep the base x and add the exponents. That's going to give you x to the fifth, okay? And then this term here, when you plug in the x to the third power and raise it to the second power, here you have a power to a power, so x cubed raised to the second gives you x to the sixth, okay? So when you do the fundamental theorem in calculus evaluation, this is where we are at, okay? Then we want to go ahead and now let's integrate every single term with respect to x. With respect to x, so this is going to give us x to the fourth over 4, all right, plus x to the third over 3, all right, minus x to the sixth over 6, okay, so now I'm going to go ahead and distribute the negative sign so I don't lose it later on, okay, all right, and then minus, and this will give me x to the 7th over 7, all right, and this gets evaluated from 0 to 1. This gets evaluated from 0 to 1. So again, fundamental theorem in calculus, we're going to plug in the upper bound. That gives us 1/4 plus 1/3 minus 1/6 minus 1/7. All right. So this is what we get when we plug in the upper bound. When we plug in the lower bound, you're going to have 0. These terms all go to 0, plus 0 minus 0 minus 0. So we just have 0 when we plug in the lower bound. All right. So your answer is 1/4 plus 1/3 minus 1/6 minus 1/7. If you want to put that in your calculator, I suppose we could do it here. We would need a common denominator, 7 and 6 and 3 and 4. So what do we have for that? 84. Okay, so 84 for a common denominator. All right, so 84 for a common denominator. All All right, so let's see how this is going to work. So 4 goes into 84, so that's going to give us, what, 21 times? So 21 times 1, so 21 over 84. 3 times what is 84? 3 goes into 8, so that's going to be 28 times. Okay, so 3 goes in 28 times. 6 into 84, so 6 into 8 goes 1's 24 left over, so 14 here. Okay, and 7 times what is 84? 7 into 8 1, so that's going to be 12 times. Okay, so when you're combining fractions, you would keep the denominator, okay, and combine the numerator. So 28 plus 21, that's 49. 49 minus 14, so 49, that's 35, and 35 minus 12 is 23, so 23 over 84. So it looks like your answer in fraction form is 23 over 84. Here is your final answer as you compute it through using the type 1 method. Right? So now what if we wanted to take a look at the type 2 method of solidness, okay? Because it can be done either way. So let's look at a type 2 solution. All right, so let's go ahead and look at a type 2 solution. Type 2 solution, so let me go ahead and sketch the base again, okay? So I'm going to go ahead and sketch the base, all right? Here's my y-axis, here's my x-axis. All right, so we have the line y equals x, and we have the cube function, okay? So these are the two, this is the two problems, okay? But up here, so this is y equals x. Well, instead of calling it y equals x, I'm gonna call it x equals y. So I'm gonna call this x equals y because, you know, we're type 2, so now we're gonna need to make our inside bounds as a function of y instead of as a function of x, okay? And then down here, we do have y equals x to the third, okay? So here, this curve right here is y equals x cubed, okay? But we want to write it as x equals so we can set up our type 2. So how do we get x by itself? We have x cubed. Well, we want x by itself, so take the cube root of each side. We take the cube root. So y, the cube root of y is what x would equal for this lower curve, okay? So this lower curve would be x equals the cube root of y when we write it, turn it around and write it as a function of y, all right? So this is what we have for these two curves right here, all right? The points of intersection, because we're going to need the bounds from the points of intersection. I'm not going to redo the algebra here. We already know the points of intersection are still going to be the origin 0, 0, and the other point of intersection is going to be 1, 1, okay? So these are your points of intersection. All right, so now let's go ahead and see what it looks like when we set up the type 2. Type 2 double integral, okay, so the integrand is still x squared plus 2y. That's still the integrand, but now we want to integrate with respect to x first, okay? So we want to integrate with respect to x, so your inside bounds, the variable bounds, have to be a function of y. Integrate with respect to x, the inside bounds have to be a function of y. And when you set up the bounds as a function of y, we're going to use horizontal slices. Let me put an arrow pointing in the direction we're going. Horizontal slices in terms of y. So when you set up your inside bounds, we're going to be going from y to the cube root of y. So the inside bounds here, you're going to go from y for the lower bound to the cube root of y for your upper bound. Okay, so this is what your inside bounds look like. Okay, then we have to set up the outside bounds. Okay, so dy, all right, so now we want the outside bounds, the y bounds, okay? So the y bounds are actually going to be the y coordinate of the points of intersection, the y coordinates, okay? Which happens to be 0 to 1 again, just because the x and the y coordinates were the same, but it is going to be 0 to 1. So there's your y coordinate, all right? So this is how you would set up your type 2, okay? So now how is it when we go through and evaluate this? Well, let's go ahead and evaluate it to see if it's easier or harder, how it relates to the first one, all right? So let's go ahead and, so we're going to integrate, remember, from the inside. We work from the inside to the outside. So we're going to integrate with respect to x first, okay? So the outside bounds, the 0 to 1, just bring it down, okay? All right, integrate with respect to x. Integrate x squared, that becomes x to the third over 3, okay? Integrate 2y, with respect to x, that's going to be 2 times x times y. Y is considered a constant, so multiply that by x. And we're going to evaluate this from y to the cube root of y, and then we'll integrate with respect to y after we evaluate this, okay? All right, so the outside bound 0 to 1, we'll be with that shortly. But fundamental theorem in calculus, now we're going to take the upper bound and substitute it in. When you take the cube root of y and cube it, that just comes out to be y. So y over 3, okay, plus we need to take the cube root of y and plug it in for x here. We're plugging it in for x. So when you have 2 times the cube root of y times y, that's going to give us 2y to the 4/3 power, okay? 4/3, because this is y to the 1/3 times y. Keep the base and add the exponents, okay? Plug in the lower bound, and you're going to have y cubed over 3, and then you're adding to that 2 times, substitute y, and y times y, so 2y squared. All right, now we're going to integrate this expression with respect to y. Okay, so let's integrate this with respect to y. So integrate the first term. All right, actually I don't need the definite integral, the balance rate set up, because we're going to do the integration now. So let's integrate with respect to y. Integrate y over 3, so integrate y, so you're going to have y squared over 2 times 3, so 6, this is the first term, okay, plus the next term. When you integrate 2, I'm bringing the 2 down, integrate y to the 4/3. When you integrate y to the 4/3, you're going to get y to the 7/3 over 7/3, or 3/7 y to the 7/3, okay? All right, so this is what you have when you integrate the first term, okay? All right, integrate the next term, integrate y cubed over 3. I'll distribute the negative sign, so I don't have to use grouping symbols. So let's go ahead and distribute the negative sign. Integrate y to the 3rd over 3. You're going to have y to the 4th over 12, okay? And then distribute the negative sign over here. Integrate 2y squared. You're going to have minus 2y to the 3rd over 3. Okay, we want to evaluate this from 0 to 1. So we want to evaluate this from 0 to 1. All right, so plugging in the upper bound. Okay, so plugging in the upper bound gives us 1/6. Okay, and then plus, when we plug in 1 and compute this fraction here, this gives us 6 over 7. Okay, minus, plug in 1 here, you get 1/12. All right, and then minus, when you plug in here, you get 2/3. Right? And then when you plug in 0, all the terms go to 0. Okay, so all the terms go to 0. And then again here, common denominator, and work out our answer. I guess we want to see that we get 23 over 84 again. So let's go ahead and get our common denominator. What would our common denominator be here? It would be 84 again. So 84 for a common denominator. All right, so let me go ahead and set this up. So 84 for a common denominator. First fraction, okay, so 6, how many times does 6 go into 84? So 6 goes into 81, so 24 left over, so 6 goes into 84 14 times, okay. 7 went into 84 12 times, and 12 times 6, that gives us 72, doesn't it? Okay. Minus 12 goes into 84 7 times, this numerator would be 7. 3 goes into 84. 3 goes into 84, 3 goes into 8 twice, 24, 28 times, and 28 times 2, so that'll give us 56, okay? So you keep your denominator, and when we combine these numerators, let's see, 72, 14 plus 72 is going to be 86, okay? 86, take away 7 from 86, and you're at 79, and 79 minus 56, 23. Okay, so 23. So here's the same way. So this is your type 2 method. This is just when you're using horizontal slices and you're integrating the x before you integrate the y. Okay, so now I did say we were going to do 2 examples. I think I'm going to put the second example in the next video so this one doesn't get too long. So this is this is how we would set up double integrals over general regions. Okay, so this is how we would set up double integrals over general regions. You have 2 methods you can use to set it up. Sometimes one method is easier than the other. Sometimes one method you could solve with one set of double integrals, and another method you might have to set up 2 sets of double integrals. So we'll do that in the next example, but here is our first example. Okay, so we're going to conclude this video, and so thank you for watching. I hope this does help. So please stay safe out there, stay healthy, and again, thank you for watching.